Hello and welcome to lesson number 2 in Unit 1, Functions in our grade 11 University College math class. So we're going to pick up with where we left off at the end of lesson number 1, which is what is a function. So a function is a relation, and recall that a relation is an identified pattern or relationship between two variables, which we can express in lots of different ways: mapping diagram, ordered pairs, table of values, graph, etc., etc. A function is a subset of relations where every input has one and only one output. Another way of saying that is that for an input value, it never changes. When we put in, say, 1 into a function, it's always going to spit out 10. It's never going to spit out 10, and then all of a sudden it's going to spit out an 8 or a 50. That's not a function. A function is something that has one and only one output for an input value. So, what better thing when you have a function than to develop a notation that helps you recognize when something is a function and save you the hassle of figuring out whether it is or is not a function, which is what we're going to be looking at today, function notation. So function notation is really just a fancy way of saying that the relationship between these two variables is so linked that we're going to give it its own notation that saves you, that sort of confers all the same information that knowing it's a function will give you, but in advance. You don't have to do any of the work for it. So let's have a look at this little table right here, which I think kind of sums it all up. Up until now, we've been working with this two variable system where you've got x, which is your input, and then y, which is the output. Makes sense. These are the axes on the coordinate plane. It's a nice, easy set of letters to understand. Input variable here of t, output value y, input x, output y, input t, output y. So we can see this, got an input and got an output. Function notation is going to save you that second variable, meaning that if you have an input, the output is just a function of the input working through the function itself. So what I mean by that is, if you look at the top two, just up here, y equals 3x plus 1, and we have this fancy little notation here, where you'll notice that our input variable is still the same, that's still x, and our output variable is our function at x. And if we look at the next one down the line, the next one was y equals 3t squared minus 2t plus 1. This one is still same input, that's a t, and then the output value is t for the function g. So what's happening in the function g at an input value of t? I'm not going to go through all these, but hopefully you see that this is the new notation that we're talking about, and it directly incorporates the input variable for the function itself, rather than giving it a whole new letter. So how do we say that? What's the terminology we're going to use? So when you see this notation here, we can read it as f of x, or, and this is my preferred one, f at x. And f, of course, in this case stands for the letter that we designated for a function. It could be g at x, h at x, really any letter that you wanted at x. It represents, in this case, we're talking about the height of the function at the independent variable x. So I like f at x. This one's sort of my preferred one. This is the one that I'll be using. I can't speak for all your math teachers. That's just two ways of saying the same thing. I like f at x myself. And again, the reason being that if we look at this guy, we've got y equals t squared minus 21. And this would be v at t. So our function v at input value t, given that this is how we're going to determine sort of where it is. So this is function notation. In terms of how function notation works, honestly, it works exactly the same as it did before, where you've got an input and an output. But let's have a look at some small changes we make here as we complete the table of value for this function, f at x equals 2x minus 1. And again, I want to point out that one of the reasons that we have this notation is so that it tells you 2x minus 1 is indeed going to be a function, meaning that for every input, there's one and only one output. You don't have to go on and do the graph and do the vertical line test and sort of figure that out. It's telling you that up front, that this is true of this relationship. Next thing I want to point out is that previously here we would have x and y. Now we have x and f at x. And you will see that these axes should be labeled x for our independent variable, and for our previous y-axis, this is now going to be f at x. Input, output. That's kind of how we're setting her up. So let's work a table of values here. here we have our input just hanging out over here, and here we have the function. And again, how does this work? We're substituting x in every time that we see x in the function notation. So f at -2, and remember that's sort of the replacement for y, so we're not doing any math over there. This isn't f times -2. F here represents our function with an input value of -2. So I'm going to sub the -2 in here for this x right here. So there it is, and when I do the math, that's 2 times -2, which is -4, minus another 1 is -5, and that I will write in here. -2, -5. And we're just going to work our way down this table. Again, if I have an input value of -1, we would say f at -1 equals, and now I'm going to do some substitution here. I'm going to change away from hot pink, I think. So we have 2 times -1 minus another 1, that's -3. So that's -1 minus 3. Again, I'm writing these like an ordered pair, but this is x and f at x. Same thing here, f at 0, that would be equal to 2 times 0 minus 1, which gives me -1. So that was 0 and -1. And f at 1 equals 2 times 1 minus 1, which gives me 1. So we have 1, 1. And last but not least, we have f at 2. So that's 2 times 2, which is 4 minus 1, which is 3. So that was 2 and 3. So now we'd go on to put these on the graph, which I'll do right now. Change up my color scheme here a little bit. So we have -2, -5. So again, I'm just watching the scale here. There's -2 and there's -5. Got it. I'll label these in a second once I see where my line's going to go. -1, -3. There we go. 0, -1, 1, 1, and 2, 3, as I recall. 2, 3, there we go. All right. So I'm going to draw a line through this, because that's what you do. There it is. Pretty close. Get some arrows on this thing. And now we'll do some labeling. That was -2. Yep, -2, -5. -1, -3. 0, -1. 1, 1. And 2, 3. All right, there you go. So again, why did we do this? The reason that we did this is just to illustrate that f at x is really just a replacement for y in terms of graphing, in terms of how you deal with it. The thing I wanted to point out, probably one of the most important things from this little segment that we just did, is right here. When you have an input and it tells you what it's going to be, again, an input here of -2, we write f at -2. It's not f at x. We're telling you that the x is -2. So we write f at -2. We write f at -1, f at 0, f at 1, f at 2. Here we do the substitution. So we would say, ultimately at the end, if I was done this one, I would just say f at 2 equals 3. If I was doing this in something other than a table, if I was just doing the calculation. And again, this is a notation. It's telling you the function at an input value of 2. No work needs to be done there. You don't, again, I don't even want to say it, but some people like try to divide by 2 here to get f all by itself. Don't do that. It's not f times 2. It means the function at an input value of 2. So you're not trying to isolate f here. So let's not do anything crazy like that. All right, let's do one more example to sort of finish up this portion of the video. We have find f at 2 if f at x equals x squared minus 2x plus 1. So we are looking for the y value, the output, when x equals 2. That's just a nice way to say that. So let's write this out. We have f at 2, so our function at an input value of 2, equals 2 squared minus 2 times 2 plus 1. And now I'm going to just follow this down. F at 2 equals, so now we just evaluate this thing. 2 squared is 4, minus 2 times 2, which is 4, plus 1. F at 2 then equals 4 minus 4 is nothing, plus 1 leaves us with f at 2 equals 1. And then we'd sum it up. Therefore, f at 2 equals 1. Handy dandy, no problem at all. That's how you use function notation. When we come back in the second part of this video, we're going to look just a little bit deeper at function notation and how we can use it, and then some of the little tricks that mathies throw in there to make it more difficult, but I'm going to show you how to navigate those. So we'll see you in part 2 of this lesson.